Okay, large language models, LLMs, they're just everywhere and getting incredibly good, right?
Absolutely, they're becoming specialists.
Exactly. You get these models fine-tuned to be amazing chat partners or like genius level at math problems or spitting out perfect code.
Hmm.
But that specialization, while powerful, leads to a big question. How do you get one model that does all that stuff really well?
Without needing, a whole data center just to store different versions.
Right? Without it becoming this massive, unwieldy thing, that's a real headache for actually deploying these models effectively.
It really is.
So today, that's what we're diving into. We're looking at a really interesting, novel approach trying to solve this puzzle. It's called one-bit merging.
That's the plan. We're going to dig into the sources you sent over, mainly a research paper from February 2025, researchers at City University of Hong Kong and Huawei Noah's Arc Lab. Plus, we've got a briefing doc, a glossary, some key excerpts, figures, tables, the whole set.
Okay.
And our mission really is to understand the hurdles. Why is combining these specialized models so hard? And then focus right in on one-bit merging. How does it work? What's the clever bit? We really want to unpack the academic innovation here, the technical details that make it stand out.
Sounds good. So fair warning, some of this might get a bit technical, but we'll guide you through the core ideas and why this is actually pretty exciting stuff.
We'll break it down.
All right, let's set the stage. We fine-tune these models, they become experts. Great. But you want that generalist, right? A model good at chatting and math and code.
Hmm.
Why isn't it as simple as just, I don't know, averaging them out or something? Why is merging these specialists so tricky without messing things up?
Well, it comes down to how that specialized knowledge gets baked into the model's parameters during fine-tuning. You're making very specific tweaks for task A and different specific tweaks for task B. When you try to just combine them, those tweaks can clash. They interfere.
Ah, okay.
And the sources really lay out the two main ways people have tried to deal with this and their problems. First, you've got what they call traditional static merging. Think task arithmetic, ties merging, DARE. These try to create one single fixed model in the end.
Okay, so one model to rule them all. Storage-wise, that sounds good.
It is good for storage, definitely. But the paper makes it clear these methods often compromise task-specific performance. There's a noticeable gap compared to the original experts.
So you try to merge your math genius and your code wizard.
And you end up with a model that's just, well, okay at both. Not great like the originals were. You dilute the expertise.
Right, you lose the magic. Okay, so what's the alternative?
The other main approach is task-specific routing. Methods like smear or twin merging, these are different. They don't make one single merged model. Instead, they dynamically choose which expert model or which set of expert parameters to use based on the input you give it.
So if I ask a math question, it pulls out the math brain.
Pretty much. And this is fantastic for accuracy, right? Because you're using the full, uncompromised specialist knowledge.
Oh, there's always a but.
There's always a but. The big drawback, highlighted in the source, is substantial storage overhead. You have to keep all those full-size specialist models or their specific parameters ready to go.
Okay, so that does sound like needing a server farm again. You need gigabytes and gigabytes just waiting.
Exactly. So you're caught. Either you sacrifice that peak performance with static merging, or you need way too much storage space for dynamic routing. That's the dilemma one-bit merging tries to solve.
Okay, that sets up the challenge perfectly. So where does the breakthrough come from? What did these researchers figure out?
This is where it gets really interesting, and it's a key academic innovation point in the paper. They didn't just look at if models learn specialized tasks, but where in the model architecture that knowledge gets stored. Through their experiments, they found something crucial. Different task-specific models store knowledge in distinct layers, such as MLP and attention layers.
Wait, so you're saying the math knowledge might live in one part of the model's network and the chat knowledge lives somewhere else?
Precisely. It's not uniformly spread out. They found specific patterns, looking at their data, like in tables 1, 3, and 11. Okay. They saw that chat models tend to store their specialized knowledge predominantly in the attention layers.
Attention layers, those are the parts that handle context and relationships between words, right? Makes sense for chat.
Exactly. But for math and code models, the crucial knowledge was primarily stored in the MLP layers, the multi-layer perceptrons, those feed-forward parts.
That's the moment, though. It's like finding out that in the brain, language processing happens in Broca's area, and maybe math reasoning uses the parietal lobe more, that kind of localization.
That's a great analogy. Yes, that knowledge localization is the core insight
And why is that so important?
because it unlocks the possibility of targeted compression. If you know the critical math stuff is mostly in the MLP layers, you can focus your compression efforts there, maybe leaving the attention layers relatively untouched for that task. The paper specifically warns against just applying uniform task-agnostic compression. They say that approach can severely degrade performance on complex reasoning tasks because you'd be damaging the very layers where that crucial reasoning knowledge is concentrated.
Got it. So knowing where the important stuff is lets you be much smarter about how you try to shrink the model down.
Exactly. And that brings us directly to their proposed solution, one-bit merging.
Okay, the main event. How does it work?
They describe it as a novel dynamic merging framework. The core idea, the technical innovation, is combining task-specific routing, like the second approach we discussed, with adaptive one-bit quantized task vectors.
Whoa, okay, lots of terms there. Let's unpack task vectors first.
Right. Task vectors are pretty straightforward conceptually. The paper defines them as the parametric deltas between PT and FT model weights. So you take your original pre-trained model, PT, and your fine-tuned specialist model, FT. Subtract the PT parameters from the FT parameters. That difference, that's the task vector.
So it's literally just the change that fine-tuning introduced, the essence of the specialization.
Precisely. It is the learned specialization. Now, the really clever part, one-bit quantization, they observed there's substantial redundancy inherent within task vectors. Lots of parameters, maybe not all strictly necessary at full precision.
Okay.
So they apply a very aggressive compression. One-bit quantization, they basically reduce each parameter value in the task vector down to just two possibilities, +1 or -1.
Just +1 or -1? That seems extreme. How does that not just destroy the information?
Oh, well, here's the crucial bit. They don't just do that. They also calculate FP16 scaling factors. These scaling factors are based on the magnitude, the L2 norm of the original full precision weights in a block. When they apply the +1 or -1 changes, they multiply them by this scaling factor. This helps to preserve the original weight L2 norm, basically ensuring the overall strength or impact of the changes is maintained even though the direction is simplified to just +or -1.
Okay, that makes more sense. It's like you're giving super simple directions, step forward, step back, but you still know how big each step should be thanks to that scaling factor. It preserves the magnitude.
That's a perfect way to put it. You compress the direction, but keep the scale.
And crucially, they apply this one-bit stuff selectively, right? Using that knowledge localization.
Yes. Remembering that chat knowledge is in attention, math code, and MLP, they can potentially apply this aggressive one-bit quantization more heavily to the less critical layers for a given task, preserving more precision where it matters most.
Clever. Okay, so you have these tiny one-bit task vectors with scaling factors. How does the dynamic part work?
They use a lightweight router. It's a small, separate neural network, just a 3-layer linear network, so it's fast. This router looks at your input query and predicts the dominant task category. Is this mostly a chat request, a math problem, or code generation?
It figures out what kind of question I'm asking.
Right. Then it selects the corresponding one-bit quantized task vector for that dominant task. Let's say it's math. It pulls the tiny math task vector. That vector is added to the original pre-trained model backbone to create essentially a temporary task-specific base model optimized for math.
And what about the other task vectors, like chat and code in this case?
Good question. For efficiency, they integrate the remaining compressed task vectors, chat and code, using a standard static method like TIS merging. So the dominant task gets the direct boost, and the others are blended in more generally.
Wow, okay, so it's dynamic selection of the main task's super compressed knowledge plus a blend of the others. That sounds really elegant, actually.
It is. It leverages the knowledge localization for smart compression and uses dynamic routing to activate the most relevant, now very small, specialization when needed.
Okay, the theory sounds impressive, really slick, but the million-dollar question, does it actually work? Does it solve that performance versus storage trade-off we talked about? What did the results show?
Yeah, the proof is in the pudding, right? And according to the paper, looking at tables 2, 5, 6, and especially figure 3, the results are quite positive. First, performance. They state that one-bit merging outperforms traditional model merging methods. It achieves broad and balanced performance across domains. And get this, figure 1 suggests it even slightly achieves superior performance across all domains compared to the individual fine-tuned expert models in some cases.
Better than the originals, how?
Potentially by combining complementary strengths. Maybe the merged model might benefit from the interaction of different knowledge types. But the key is, it's performing really well, not compromising like the static methods.
Okay, that's huge for performance. What about storage? Did they beat the routing methods there?
Yes, that was the other major goal, and they report better storage efficiency than task-specific routing approaches. Let's pull some numbers from the Mistral 7b experiment shown in Figure 3, merging chat, math, and code. Compared to keeping the full parameters for dynamic routing, one-bit merging maintained 94.53% of their performance, so very little performance drop.
Almost identical performance.
But it reduced the storage requirements down to just 55.02%, nearly cut the storage in half.
Wow, okay. That's a massive improvement in efficiency. Figure 3 probably shows that point way off in the desirable corner, high performance, low storage.
Exactly. It plots performance versus storage, and 1-bit merging sits much closer to the high performance of full routing, but uses significantly less storage. It really hits a sweet spot.
What about other compression ideas? Did they compare it?
They did. They compared it specifically to SVD compression, which is used in methods like twin merging. That's in Table 4. They found that SVD, while a valid compression technique, seemed to struggle more with capturing the really fine-grained information needed for complex reasoning, especially in math and code. The 1-bit quantization with those scaling factors seemed better at preserving that critical fine-tuning knowledge.
Interesting. So the specific way they compress matters a lot.
It seems so, and they also showed it wasn't just a fluke with one model. Table 6 shows it works well across different architectures, Mistral and LLaMA2, and at different sizes, 7 billion and 13 billion parameters. The benefits were consistent.
Okay, this really does sound like a breakthrough then. They pinpointed where knowledge lives, developed a super aggressive but smart compression for it, the 1-bit plus scaling, and dynamically activated the tiny relevant piece. Best of both worlds almost.
It certainly looks like a very promising direction, achieving a much more favorable balance than we've seen before.
So thinking bigger picture, what's the real significance here?
Well, the paper frames it as a significant advancement in efficient LLM deployment. Essentially, it makes it much more practical to deploy a single LLM that has multiple specialized capabilities. You get the versatility without the crippling storage demands of keeping multiple full expert models around.
Which for you listening could mean a few things down the line. Maybe more capable AI assistants on your phone or laptop because they can pack more skills into less space. Or cheaper cloud services running these powerful, versatile models. It makes advanced AI more accessible.
Definitely potential for that. But like all good research, the paper is also upfront about limitations. Science is iterative.
Always important to remember, what are the caveats?
One key point they raise is the lack of a comprehensive theoretical understanding. We have strong empirical evidence now that this works, but the deep theory of why combining weights this way, especially with quantization and scaling, is so effective is still being developed. It's more, we observe this works well, than we have a perfect mathematical proof for all cases.
So, still some fundamental questions to explore there.
Right. And the other major practical constraint is architectural. This method, because it directly manipulates and adds parameters, the task vectors, is currently restricted to models sharing identical architectures.
Ah, so you can merge fine-tuned versions of Mistral 7B, but you can't usually merge a specialized Mistral with a specialized LLaMA using this technique.
Exactly. They have to have the same underlying structure for the parameter addition to make sense. Merging models with fundamentally different architectures is a whole other, much harder challenge for future research.
Okay, what a journey. We've really taken a deep dive into one-bit merging today. We saw the core problem, that tension between specialist performance and storage efficiency. We uncovered that fascinating insight about knowledge being localized in different layers, attention for chat, MLP for math and code.
A critical piece of the puzzle.
And then we unpacked how one-bit merging cleverly uses that insight for targeted, super aggressive one-bit compression combined with dynamic routing to get impressive results.
It's a really elegant example, I think, of how digging into the internals of these complex models, right down to the layer and bit level, can spark these really practical innovations. It's not just about making them bigger, it's about making them smarter and more efficient.
Absolutely. And it leaves you wondering, doesn't it, this idea that different layers handle different knowledge. What else could we do with that?
Hmm.
Could that insight lead to LLMs that are even more modular, maybe easier to update just the math part without retraining everything? Or could it even help us understand how they reason, make them more explainable?
That's a great question to ponder. It definitely opens up avenues beyond just merging. Lots to think about and explore based on the work in these sources.